that they move. We talked about ions, which is actually electrons leaving or joining a totally different atom. Today we're going to talk about electron excitation, which involves electrons moving around within and within the same atom. This is not electrons being gained or lost. They are actually still within the same atom. So this doesn't have to do with charges or anything like that. It just has to do with electrons finding themselves at a different address. So basically just going over to somebody else's house, they're going to come back home later. So exciting electrons live in what we call principal energy levels, remember. So I'm going to continually abbreviate that. PELs is a lot shorter and a lot easier. They're not stuck in a particular PEL. They're able to move. They're moving actually all the time. So remember, keep in mind, PELs that are closer to the nucleus have lower energy. PELs that are further from the nucleus have higher energy. The capacity or the size for a PEL, how many electrons it can hold, is related to location. Further from the nucleus, you're going to have larger PELs, and therefore they can hold more electrons. Now this really is, we depict this as circles. It's not completely true, but there's kind of a spherical nature to it. So the outside of a sphere has a lot more area to hold things than an inner part of a sphere. How many electrons can each PEL hold? Now, I'm going to show you actually a calculation for this. It's not something that you need to memorize. You can figure this out from the periodic table. Your first PEL, if we follow this little formula that tells us our maximum number of electrons, 1 squared times 2 gives us 2. If you look at your periodic table, the first PEL always has 2 electrons in it. Now, again, once you get down to number 72 and beyond, a lot of people say, hey, that starts with an 18. It doesn't. There's an asterisk there. It says denotes the presence of 2-8. So there really is only 2 electrons in that first principal energy level. Our second principal energy level, 4 times 2 is 8. So if you look at all your second principal energy levels, the biggest number you'll see there is 8. Don't forget your PEMDAS here. 3 squared is 9 times 2 is 18. Again, you'll notice that if you look through your periodic table, 32 for our fourth principal energy level, and 50 for our fifth principal energy level. So if you go through and look at those, obviously the fifth principal energy level, we don't have a lot of those being filled up, but our smaller principal energy levels we do, so you can see that you'll see a lot that are maxed out at 2 or 8 or even 18. Again, you don't need to memorize this formula because if you need to know how many maximum electrons are in a principal energy level, you can just look at the periodic table and figure that out. When an electron becomes excited, this has to do with it moving on those rungs of the ladder. We start with what's called the ground state. This is the lowest energy configuration for an atom. Ground state electrons, or ground state electron configurations, are what we find in the periodic table. So the configurations that we've looked at so far have all been ground state electron configurations. If an electron absorbs energy, it can move to a higher principal energy level. So it can go up on the ladder, if you will. We can give an electron energy by through electricity. That's actually how light bulbs, traditional light bulbs function. We can also cause an electron to move up by giving it heat. So like a flame tester, a firework works that way. This move is going to change the electron configuration. So it's not really in that true ground state that we saw on the periodic table anymore. The new configuration is what we call the excited state. So we'll draw some Bohr diagrams to see what this looks like. So if we wanted to start with sodium, okay? Sodium is a great example, nice simple 2-8-1 configuration. That's the configuration on the periodic table. It's a ground state configuration. So I'm going to make some little electrons here the lazy way. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, configuration because we just pulled it off the periodic table. I'm going to do this the lazy man's way. Sorry, you have to do this the not lazy man's way. But if we want to excite one of these electrons, all we got to do is move it up. So I'm going to take one of these guys right here, okay, see this guy, and I'm going to go like that. That's an excited state configuration. Bam, done. So my ground state configuration was 281. This new configuration is 272. Now I want you to notice, sodium has 11 electrons when it's an atom. This sodium still has 11 electrons. We didn't change the number of electrons that we had. There are some things that you need to be careful of when you're making this excited state configuration. So if we start with this initial configuration that we had, you might be tempted to move one of these guys up, okay? And that would give me the configuration, that would give me the configuration 191. Now, I still have 11 electrons there, so that's cool, but there's a problem with this. So what you might notice is we have 9 electrons there. Our second ring can really only hold 8 electrons. So this configuration can't actually occur. That one electron that we moved up, it could go out to this outside ring. So an acceptable configuration could be, oops, I keep wanting to write 2, 1, 8, 2. We still have 11 electrons. You can even move these guys out and make a whole other PEL out there. You know, you kind of have some freedom with that, but I like to kind of keep it simple. So we can go ahead and we can start with this 281 configuration. You should be able to list the different configurations. I like the very simplest one of all. That's my favorite one. Another really simple one we just did is that one right there. Based on our starting one, we hit the 2, we could go down to 6 here, and so we have 3 right there. Remember, overall we have to be careful. We should always have 11 electrons, and we can't overfill any PEL. So it's especially important. The second one, it's really easy to plop 9 electrons in there. Don't do that. So I like to keep it simple and just kind of take one from the second to the outside ring and move it to the outside. If you wanted to get crazy on this one, you know, you can do 2, 6, 2, 1. You know, you can do some other different stuff. You can have 1 dash 1 dash 1, but it's easy to make mistakes, so be careful. For an electron to move up to a higher principal energy level, it has to absorb energy. So I'm going to put a couple of electrons on here, or actually I'll just use the one right there. So for electron to move from here to here, energy was actually put in form of heat or electricity. And now that electron's at a higher energy level, it's farther from the nucleus, it has more energy now. Now that same electron that we saw up there in the second principal energy level, if it wants to move back down to its home, which it's going to want to do that, it's going to actually have to emit energy to go back to that initial ground state configuration. And typically it does this in the form of light. So we're going to look at some spectra, which are actually how Bohr knew that electrons at energy levels, which are basically that light being given off by electrons moving down to a lower energy level. So what's important to be able to explain is that when an atomic emission spectra is produced, it's produced by an electron, you know, absorbing energy and moving up to a higher principal energy level. The light we actually see, though, is when that electron falls back down to the ground state. So I really like this little explanation online. We have a ground state atom right now. There's just one electron. It's in the very lowest shelf it could possibly be in. To put this in the excited state, energy would be absorbed, and we'd see an electron move to a higher state. So it went from the first level up to the third level. So what this actually looks like when we look at atomic emission spectra, we have a whole bunch of hydrogen atoms being shown in this graphic. And all of them are in the ground state. There's one electron. It's on the very lowest possible shelf, which is the first principal energy level, or what they're calling here N equals 1, so our first energy level. If we put energy energy into these atoms. It will excite the electrons. Now, what I want you to notice is they don't all go to the same energy level. So this one jumped from 1 to 3, this one went from 1 to 4, 1 to 5, 1 to 6. So they all actually absorb slightly different amounts of energy and move to slightly different places. And they're going to fall back down. Now, the reason that they do this is like, what would happen to you if you slugged a bunch of Red Bulls in the morning and then came to school? You would eventually have kind of a crash. So it's not the natural state for these guys to be in that high energy state. They're very unstable there. So they actually go and fall back down. Now, when they fall back down, they give off energy. Now, what you're going to notice, and we're going to look at these in classes, there's only specific amounts of energy given off. So if we go back to where we were before for a minute there, the guy all the way over on the left, he actually doesn't go all the way to the ground state. He's just going down 1 PeL. This guy's going to go down 2 PeLs, 3 PeLs, 4 PeLs. And the distance that they fall actually affects the color of light that they give off, because color of light is related to energy. So this is something this is actually what Bohr saw that told him, hey, electrons only fall these really specific distances. That means something. That means electrons can only be on certain energy levels. So we'll talk more about that in lab. There's also, again, how things like fireworks work. So you need to be able to give a nice explanation of how atomic emission spectra are produced. So what's important to say is that you're starting with an atom in the ground state. And that atom in the ground state is going to absorb energy. This causes the electrons to move to the excited state. The electrons are then going to fall back down to lower energy levels, or the ground state, and give off energy. And they will give off that energy in the form of light. Now, you do need to be able to kind of spit this explanation out. So you kind of reword it, gently so that it kind of fits your own wording a little bit better. The key idea is here that first energy is absorbed, that excites the electrons, and then those electrons fall back down and release light. What's also very important to keep in mind is what you're actually seeing, that light that you actually see, is from electrons falling down. It is not from them absorbing the energy and moving up. So the actual spectra that you see is because of the electrons falling back down, not because of them moving up